Thanks, Meg. And thank you, everyone, for coming out early on the Friday. Glad you made it to day 3. So following up on Meg's presentation, focusing on ICM, I'm going to mostly be talking about how we built a cross-chain transfer protocol on top of ICM called ICTT. But just to start off, to make sure we're all on the same page as far as the names that we're referring to, because some of them have changed recently. If you've made it to day 3 of Summit, I'm sure you've heard that subnets have been rebranded to Avalanche L1s. You might not have heard why that's the case. So before the Etna upgrade, all subnet validators are required to also be primary network validators, which makes the subnet validator set a subset of the primary network validator set, hence subnet. But with Etna and ACP 77, that's no longer the case. So it's technically incorrect to call these networks subnets anymore. They are their own sovereign L1 chains with their own independent validator sets. And so that was the technical motivation behind that, not just pure marketing. The 2 other names that I want to make sure we're on the same page about going forward into the presentation are Avalanche Warped Messaging and Teleporter, which are now both under the Avalanche Interchain messaging umbrella. I think Meg did a great job of describing the difference between these two. Interchain messaging, I think, gets right at the heart at what it is. It's very self-descriptive, so we don't have to go into detail there. Warped messaging was the primitive that enables it. Teleporter is the Solidity components that make it easy to integrate with. So our mission today, to hopefully guide us through the presentation, is that we want to be able to efficiently launch your sovereign L1 blockchain and immediately be able to transfer existing liquidity in and out of it securely. So there's a lot of components to this. The first part, efficiently launching your sovereign L1 blockchain, that gets more towards ACP 77 and making it as inexpensive as possible, removing the 2,000 Vox validator requirement. The second part is really the heart of this presentation as far as ICTT is concerned, being able to move existing liquidity into your own L1 efficiently, securely, and immediately. You don't need to get any third-party integrations. You can do it all yourself and have it be secured by the validator set of your network and your network alone. So to start off, just we'll touch upon Avalanche Interchain messaging again to go I think, into a few different properties of it that made it great to use to implement Avalanche ICTT. So I will talk about the kind of end-to-end flow of a message a bit more, expanding on Meg's presentation. And I think this is important to kind of have as the foundation when thinking about ICTT, since ICTT is just a specific application built on top of ICM. So we get the general message passing from ICM, and then ICTT is the token transfer on top of it. So first, as Meg referred to, it's enabled by the Avalanche P-chain. The P-chain acts as a validator registry for all L1s. It's synced by all L1 nodes, and that means that all L1 nodes know of other L1's validator sets. And when you register your validator on the P-chain, you include your BLS public key for your validator and a proof of possession of that public key. And this makes it such that L1s are able to uniquely identify the validators of any other L1, and it provides a read-only view of the current validator set as such. The read-only part is interesting here. I think we briefly touched upon it earlier, but it makes it such that you are able to verify ICM messages on your L1 without putting any load on the primary network at all. Because you have a local copy of the P-chain state on your node, all you're doing is a local read of whatever the current state of the P-chain is. There is no writing to the P-chain in order to either produce or verify an ICM message. So the BLS signatures are definitely, I think, one of the better engineering decisions we've made in the past few years. As Meg got into, they provide a synced attestation of any validator, of any message from a chain's validator set. And so just to kind of take a step back here and walk through the end-to-end flow again of a message. When a message is sent on one L1, sent, it might be a bit of a misnomer because there's no real action taken on behalf of a validator to send a message. Sending a message just means making the validators willing to sign this byte array using their public key. And the way that this happens in ICM is that a special event is emitted in the context of the EVM that the validators know to listen for, and when they see that event get accepted on chain, they just insert whatever bytes were included in that message into their set of messages that they're willing to sign. Then, once that source chain transaction is accepted, an off-chain relayer aggregates signatures from those validators, and they query the validators for their signatures using the ACP 118 interface. So when we were implementing ICM, we realized that this is kind of the nitty-gritty of it, and it kind of gets very tricky very quickly to know how to actually query a validator for their signature of a given message. It might not just be the message ID that you would like for the message to be signed. Different VMs have any number of different use cases, and the ACP 118 interface tries to make as few assumptions as possible. It's a best practice for VMs to implement. It's not necessarily required, but it makes it such that it is super easy for any off-chain relayer to query your validators for signatures over any message and prove to those validators why they should be willing to sign it. One aspect of the relaying that I think is important to touch upon is that anyone can be their own relayer or run their own relayer or provide relaying services for others. It is a completely open framework. This might make the fees a bit more confusing because you need to know who you expect to relay your message in order to know if you need to pay them or not. But we made as few assumptions as possible and wanted to make it as open as possible in this sense. And then since anybody can be their own relayer, they can also then put that aggregate signature that they get from the source chain validators into a transaction, which is they broadcast on the destination chain. The destination chains all verify the signatures by referencing the p-chain state. So like I said previously, all L1 nodes sync the p-chain, and that makes it easy for them to look up the source chain's validator set, get the public keys of those validators to be able to verify the BLS aggregate signature. So a few unique properties of ICM that I don't think we've touched upon yet is how flexible it is. So when we think of general message passing protocols, it really, I think what we touch upon most frequently is this first type of message, this event occurred. So that's really what any smart contract, cross-chain smart contract application needs. For a simple bridge, the event, it will be a locking of tokens on one chain, and that triggers the sending of the message to mint the tokens on another chain. Or the event might be the burn of those tokens to trigger the release back on the source chain. But there are other basic message types that we could use in ICM that I think are also very interesting. Validators can sign that an event hasn't or won't occurred, which is definitely something that I think has been underexplored to date, but we do use this in the ACP 77 flows for proving that a validator can never be added, or a specific validation ID will never be active on the p-chain. So it's a unique inverse for those messages that you can use for a number of different applications. And then another type of message that also hasn't been touched upon as frequently are what we call off-chain messages to support governance use cases. And this is more of the type, this action is authorized. So you can use ICM messaging to authenticate actions or gate actions behind authentication from a validator set of any L1 on Avalanche. It's pretty interesting to think of all the possible applications of this. We developed a validator set signature contract, actually, which we have recently published, and it lets you, it's very similar to Gnosis multi-safe setup, where instead of explicitly having to identify the addresses that participate in the multi-sig, you just specify the L1 that must provide a valid aggregate signature from its current validator set in order for that action to take place. And these messages aren't sent on-chain at all on that L1, but they would just need to be signed off by a threshold of the chain's validator set. And they can approve of those messages by manually adding them to their configuration. So you can get really unique governance use cases. You can change chain dynamics gated behind this type of authentication, such as changing fee rates or any really DeFi possible DeFi applications that I think will be exciting to see come about. Finally, ICM is fully open, so any L1 can verify messages from any other L1. That is obviously a critical component of this. It's all point-to-point. There's no reliance on other integrations or other chains that you need to either allow list or run a light client for your chain in order to be able to verify messages from you. As long as you are posting your validator set to the P chain, which all L1s do, any L1 will be able to verify messages from you. You can connect your L1 to the C chain on day 0 because of this. This was something that we thought was critically important. We shouldn't need the C chain to explicitly approve of your L1 or trust your L1 in any way. The ICM primitive provides authentication for messages, and that's it. It exposes to the virtual machine that this source chain signed off on this array of bytes. Smart contracts then are what define the effects that the messages have. And so one question that I've gotten a few times that's really interesting in this area is, okay, what if I launch my own L1? I am the only validator for this chain. I am running the validator on my laptop, and I decide to be malicious and send a message to the C chain that didn't occur. I just forge a message and send it to the C chain. Is that going to be verified? And the answer is yes. The C chain will absolutely verify that message and expose it to the EVM saying this L1 signed this message. Now you might think that's really bad, but it's actually not because of the fact that the smart contracts define the effects that the messages have. So in this case, if you launch your own L1, sure, you can prove to the C chain that you signed any message from your L1, but that message can't have any effects beyond what your L1 has been programmed to do in smart contracts on the C chain. So let's take a bridge, for example, here. You launch your L1, you move $10 of USDC from the C chain into it, and now you forge a message from your L1 saying, actually, I want to redeem 100 USDC. The smart contract, the ICTT smart contract on the C chain, which we'll get to in just a little bit, is going to revert because you have only moved 10 USDC into your L1. Sure, you can corrupt your L1 if you'd like and try to steal the funds that have been moved into it, but this is the fault isolation properties that L1s provide. They are fault independent of one another. If there are or is a insecure L1, yes, the funds on that L1 could be corrupted, but it shouldn't affect any other chains. And the fact that ICM allows these messages to be verified and doesn't need an allow list to receive messages from any other chain, I think makes it far more appealing to new chains that are just getting started. You don't need any special permission. Great. So now that we have ICM, the foundation of ICM, I'm going to talk about how we built token transfers on top of it. So ICTT is a Cross-L1 transfers framework designed and built on top of ICM from first principles. Those are that we can move tokens from any L1 to any L1 with no double wrapping. It's extensible for custom use cases. You shouldn't be forced into any representation of a certain token on your L1. You can represent it however you'd like. And it supports intents, which is the send and call feature of ICTT. So to begin, when we talk about cross-chain transfers of tokens, it's important to conceptualize a token having a home chain. This is the chain that the token is originally issued on. Today, for many tokens, that is the C chain, but there's no technical requirement for that to be the case. I think we would like to see more and more liquidity being issued directly on L1s in the future, and you can move tokens from the home chain to any other L1, which we would call a remote chain, just the chain that it's not issued on. And this is a pretty standard bridge transfer. You would go from the home chain where the token is issued to a remote chain where it's issued as a wrapped token of some sort. And then you can burn the token on the remote and redeem it back on the home chain. With ICTT, though, you can have any number of remote chains. This is from any L1 to any L1. So if you launch your own L1, you issue a new, you're running the EVM, you issue your own native token in that EVM, you can move it to the C chain and represent it as an ERC20 there, or you can move it to any other L1. And once you're on that remote chain, the next question is, okay, what if I want to go not back to the home chain, but to another destination? If we're having thousands and thousands of L1s, you're not necessarily going to always want to just move back to the home chain and then on to the destination. And the question that we had to ask ourselves is if we want this connection to be direct or to go through the token home. The reason why we ultimately chose to not include that connection is because if we include it, all of the remotes would have shared security. And by that, I mean, if we take an example, if we take an example of a USDC on the C chain, say, and move it into my L1. Now, if I go from my L1 to, say, Meg's L1 and want to go from Meg's L1 back to the C chain, all the C chain knows is that 10 USDC were moved into my L1. And if the C chain were to allow Meg's L1 to redeem those tokens, me and Meg's L1, or our two L1s would be interconnected on a trust level in the sense that if Meg's L1 was corrupted, that would affect the liquidity that had been moved into my subnet. And that was just an unacceptable design principle for us. So instead, to support from any L1 to any L1, when you want to move from remote 1 to remote 2, you specify remote 2 is my destination chain. That is where I'd like to end up. And the message that is sent from token remote 1 is automatically routed through the token home contract where the accounting balances are updated. So the token home knows that my L1 is no longer able to redeem these tokens, and token remote 2 will now be where those tokens exist. And the great thing about this is that, like I said, you only need to specify the destination, or as a user, you only need to specify the destination where you'd like to end up. When you start this transfer, this routing happens automatically. When the first ICM message from token remote 1 to token home is executed on the token home contract, it, like I said, updates the accounting balances and then sends a second ICM message on to the ultimate destination. And we can extend this to arbitrarily many token remotes, so you can go from and to any L1s with no double wrapping between them. So I touched upon this briefly already, but when you launch your own L1, you get to define how those tokens will be represented within it with just a single, if I go back, single token home instance for a given asset, say USDC on the C chain. You can represent it in arbitrarily many ways across all these different L1s that are the remotes for the, in this case. It could be a basic ERC20, which I think most bridges have gone with thus far. You could provide your own custom ERC20 logic, be it a block list or any other authentication or regulatory focus mechanisms. It could be the native token of the EVM, or it could be some token representation that we don't even know of yet today. It should be extensible for any tokens that basically are able to be locked and minted. There are a few interesting considerations that I wanted to touch upon for the case of the native EVM token here. So one, when the ICTT token remote contract receives tokens to be issued as a native token, it must be configured with the native mint to precompile to have the access to mint the native token of an EVM. This was a modification to the EVM that our team implemented to enable a use case just like this. And then finally, there's a bit of a chicken and the egg problem here, because in order to launch your L1, you have to issue some amount of the native token to produce any blocks originally. So you need to pay the gas fee for any given transaction. In your Genesis block, you must provide, or you must allocate some small amount of tokens so that anyone can send the initial transactions on your chain to be able to move more tokens into it. While this was a little unfortunate, we kind of abstracted it away in the contracts. So the initial number of tokens that are allocated in the Genesis are under collateralized on the token home because you created them out of thin air. But before any transfers can be performed in and out of your native token remote contract, the contracts enforce that you need to provide that amount of tokens that were allocated in the Genesis on the home chain such that it's fully collateralized going forward. So in practice, what this looks like, say if you wanted to use USDC as your native gas token, you allocate 10 USDC out of thin air on your new L1 in the Genesis. But before you can move that anywhere, you must provide that 10 USDC on the C chain, lock it in the contract, and then going forward, you're fully collateralized just like any other bridge. And our tooling team has made the deployment and collateralization steps of these setups super easy using the Avalanche CLI. So this is the command that you can run on your new L1 to get it all set up properly. So the final feature of ICTT that I wanted to talk about is support for intents. So transferring tokens across chains is great, but using tokens wherever and however you'd like is better. The use here that we're referring to could be a cross-chain swap. It could be using tokens to pay for fees for services on another chain or paying back a loan on another chain. You shouldn't need to explicitly bridge your tokens first and then put them to use. You should be able to say what you intend to do with your tokens once you bridge them, all in a single transaction. So this is implemented using the send and call interface, where you basically just get to specify not only the amount of tokens that are getting bridged, but the input data, which says where the token should end up, and has the arbitrary call data that will be provided to that contract that can be executed to put your tokens to use however you would like. On the receiving side, they just have to implement the receive tokens interface. And this payload right here is where the arbitrary data is encoded. If you're doing a cross-chain swap, that's where you would specify your intent for which asset you'd like to move into and your allowed slippage, et cetera, et cetera.
Hey, Michael, I want to cut you off in case there's any questions.
Good, just 2 more slides.
Okay, all right.
Thanks. I think we have someone here from the Tesseract team, but wanted to highlight this because I saw it just on Monday and was super excited by it. They're already using ICTT send and call to build cross-chain swaps, so shout out to them. And then just to wrap up, wanted to put this all in context of Avalanche 9000 a bit, zoom out to the bigger picture. So cross-chain messaging and cross-chain token transfers are definitely a core part of the Avalanche interoperability vision, but it's just one piece of the larger 9000 picture. These are all of the ACPs that are included in Avalanche 9000 in the Etna upgrade. I'm not going to touch upon them all because that could go all day, but would be happy to speak with any of you all about them afterwards. This is a link to the ACP repo that discusses all of them. And one high-level point that I would call out is that these are all focused on making it as easy as possible to launch your own L1 and move the liquidity in and out of it. So there's not only larger changes like ACP 77, but a lot of smaller UX improvements that we have been making along the way and would love to have feedback on, or if you have any ideas for how we can further improve it, definitely feel free to open ACP. Yeah, that's it. But also, if this sounds interesting to you and you think you could come help us build it, that would be great. Here's a QR code to all of our open positions currently. So wanted to give a little shameless plug for Ava Labs there. But yeah, thank you so much for attending and happy to answer any questions with the time we have left.
Classic engineering manager plug. Come work with us. Any questions? Okay.
Thank you. Thank you. One question I have regarding, very basic one probably, but for L1 to be able to use cross-messaging, the validators of the L1, they have to register on the P chain. That's one thing. But do they also have to stake through the P chain as well? Because we want to know the active validation set anytime.
So you do not have to stake the primary network, if that's the question. You can be an L1 validator and not validate the primary network at all, and still verify messages from any other L1, and any other L1 likewise will be willing to validate messages from your validator set.
But how does P-Chain know that the active validation set of L1, any given L1?
Yeah, so that's baked into the platform virtual machine, which the P-Chain uses. When you register your L1 validator, you post I think it's register L1 validator actually, transaction on the P-Chain that includes your node ID, the weight of your validator in the context of your L1, your BLS public key, and the proof of possession of it. So anyone syncing the P-Chain is able to does replicate the state of each L1's validator set just by tracking those transactions. Yeah, happy to talk in detail about it.
I think we're out of time, but Michael will be happy to talk about this for the rest of the day. So please go talk to him about it. Thank you.
Can't wait. Thanks, everyone.